In 7.2 we talk about rational exponents, but before we even do that we want to review some exponent laws from before. If you're multiplying and you have the same base, remember you add the exponents. So for example, if I have x squared times x cubed, that's going to give me x to the fifth. If you're dividing and you have the same base, remember you're going to subtract exponents. So for example, if I have x to the fifth over x squared, that's going to give me x to the 5 minus 2, which is 3. If I have a product inside shared to an exponent, the exponent applies to both. So that's a to the m, b to the m. For example, if I have 2x, everybody raised to the fourth, for example, that's going to be each of the guys is going to get the power, and that's going to give me 16 x to the fourth. Same thing for a quotient, they both share the exponent, so I have a to the m over b to the m. For example, if I have 2 over x raised to the third power, they both share that exponent, and I get 2 cubed over x cubed, which is actually 8 over x cubed. Recall, if I have a power raised to another power, then the exponents actually get multiplied and I get a to the mn. For example, if I have x squared raised to the third power, then these guys multiply and I get x to the sixth. Don't confuse that with up above. If I have both of them multiplied with their own bases x, you add the exponents. 2 plus 3 is 5. Whereas if I have x squared dangling to a third power, then you multiply the exponents. If I have any non-zero base raised to the 0, the answer is always 1, remember. So if I have something like x to the 0, I get 1. Or if I have 10 to the 0, I get 1. If I have a negative exponent, that implies reciprocals, so that actually turns into 1 over a to the positive n. For example, if I'm looking at 2 to the negative 3, that's really 1 over 2 cubed, which is 1 over 8. So negative exponents, say, create reciprocals and move them either to the bottom or the top accordingly. For example, part H kind of comes from part G, where negative exponents mean reciprocals and you move them up and down and the exponents become positive. For example, if I have x to the negative 3, let's say 2x to the negative 3, y to the negative 2, I have 2 times that, so the 2 stays where it is, the y goes up and becomes a positive 2 exponent, the x to the negative 3 goes down and becomes a positive exponent. So these are all the properties from before that we must remember before I even go to rational exponents, which means exponents with fractions. So all these properties must be reviewed and you must be comfortable with them. So let's look at the next topic, the actual topic, which is rational exponents, which really means fractional exponents. And the minute you see fractional exponents, you should think, oh, I'm just looking at radicals. So the first property we're going to look at is if I have a to the 1 over n, that's actually really just nth root of a. So again, anytime I have a fractional exponent, think of it as radicals. For example, let's say we have to simplify. Let's look at 4 to the half. Well, anytime you have 4 to the half, this actually implies that's the root, whatever's in the denominator. So I'm looking at the square root of 4, which is just 2. Or if I have a to the 1/3, all I'm looking at is really the cube root of 8. So that's going to be cube root of 8, which we know from before pops out a 2 again. So fractional exponents simply to you mean think radicals. Let's look at some more examples. So now I have all of negative 27 raised to the 1/3 power, and all you look at is really the root, so I'm looking at cube root of negative 27, which pops out a negative 3, because negative 3 times negative 3 times negative 3, negative 3 repeated 3 times, multiplied gives me a negative 27, so the answer that it pops out is negative 3. Now I have negative 9, all of it raised to the half power, and remember that's the index, it's the nth root, so I'm really looking at the square root of negative 9, which you know is not real, because no number times itself in the real number system is going to give you negative 9. So not real or undefined. Now this time, pay attention to the half, which applies only to the 16, and the negative is going to wait outside. E is different than D because D have the parentheses, so everybody got raised to the 1/2. What I end up with here is square root of 16 with the negative waiting outside, because the half only applies immediately to 16. Well, this we know is 4 times 4 gives me 16, so a 4 pops out, and then the negative waits in front of it. So E is different than D. How is F different than these? Well, the negative 1/2 applies to all of 64. However, remember negatives mean reciprocals, so I'm really looking at 1 over 64 to the positive 1/2, because I don't like that negative exponent, which is really 1 over square root of 64, which pops out a 1 over 8. So earlier we looked at property 1, which had a to the 1 over n, and the easy thing was that the numerator was always 1 and the denominator was the nth root. Property 2 says a to the m over n, so the numerator is no longer a 1. And when we do this, it's equivalent to nth root of a to the m, which is equivalent to nth root of a the m outside. All three items are equivalent, and an easy way to remember this is to think of flower power, which is what my high school teacher taught me. So if you think of flower power, imagine a flower next to the power, a flower next to the power, and whatever's above with the flower is the power, and whatever's with the root is actually the root of the problem, the nth root. So power and flower above, root in the bottom. If you just remember that, then these two pieces are not going to be that hard to remember. Let's look at some examples. So here's what I mean. I'm going to draw my little flower next to the power, which means I have 8 with a root of 3 and a power of 2. Now what's cube root of 8? Cube root of 8 is 2. With a power of 2 waiting outside, my answer is 4. So all I did was use the flower power. Or you can think of it like this. Again, the root is 3 and the power is 2. You can put the power inside if you want, and if you put it inside, it becomes cube root of 64. But remember, 64 is 4 times 4 times 4, and if I have 3 of them and it's a cube root, one of them pops out and I get the same answer as I did before. So whether you put the power under the radical or outside, it doesn't matter. Let's look at part B. So I'm going to draw my little flower with the power and then the root. I have the root, a square root of 4 with a power of 5. I'm going to put it outside because it makes it easier. Smaller numbers to work with that way. Square root of 4 is 2, and then the power 5 outside. 2 to the 5th is just 32. 2 times 2 times 2 times 2 times 2 is 32. If I put the 5 under, 4 to the 5th is going to be kind of big to deal with. I would rather deal with the 5 outside as my power. Let's look at a couple more. Remember 2/3 applies to the whole inside, and I have my power upstairs, my root downstairs, so I have a cube root of -8, everybody to the power of 2. That's going to pop a -2 because -2 multiplied 3 times gives me -8. I have a power of 2 waiting outside, and -2 squared is 4. Again, part D, the power applies to everybody inside the parentheses. However, I don't like that negative exponent. I would like to take care of that first and deal with the reciprocal. So take care of the negative exponent. Now apply the negative exponent to everybody with your flower power business. So I have 1 over a root of 3 of -8 then squared. So that's going to be 1 over, the inside pops out a -2, and then I have a 2 waiting outside, so ultimately we get 1/4. So they're similar, C and D, it's just that D is the reciprocal of C. Write each one of these in radical form. So remember, this is just a square root of 10, and it didn't say to do anything further. I'm done. Remember, this is a 4th root of y, and again, there's nothing more I can do, so I'm done. With this guy, I need to take care of the negative exponent first by writing it as a reciprocal. Then if I do my flower power, I have the root to be a 4 and the power to be a cubed, so I can put 1 over 4th root of b cubed with the cubed either inside or outside the radical, it doesn't matter. Alright, simplify and assume all variables are positive. That means no absolute value is needed because everything that gets popped out is going to be positive anyway. So I don't need any of these absolute value bars. Write the answer with exponents. So first of all, I'm going to say they each share the -1/2 exponent. And once I have a power raised to a power, remember I multiply them. So that's going to be x to the -1 and y to the -3. And now they're in the wrong place. Y needs to go up to become a positive exponent, and x needs to come down to become a positive exponent, and we're good to go. Part B, I'm going to work inside out. I'm going to deal with this guy first and say, well, that's just y to the 1/2 because I'm dealing with a square root problem. Now I'm going to focus on this because I have the inside raised to this other radical. So let's make that a different color. So I have the inside, I'm going to think of that as y to the 1/2, but the y to the 1/2 was trapped under the radical, and that radical itself is another 1/2 exponent. Now, like part A, I have exponent raised to an exponent, so I really have y to the 1/2 times 1/2, which is y to the 1/4. And since they said write with exponents, I'm going to leave it as a y to the 1/4. If they said with radicals, then my answer would be 4th root of y, because 1/4 really means it's a 4th root problem. Part C, to simplify, it looks like I have a monomial looking thing times a binomial looking thing, so I have p to the 1/2 times p to the 3/2 plus p to the 1/2 times p to the 1/2, and since they have the same base, I'm really adding the exponents, and since they have a common denominator, that's even better. I have p to the 4/2, which is just p squared, plus p to the 2/2 when I add the numerators, which is just p to the 1. So I really have p squared plus p, which I can't do anything else with because they're not like terms. So that's the best I can do with that one.